we've been talking about Taylor and Maclaurin polynomials, and what that leads us into, okay, because remember we talked about these expansions that we have addition and or subtraction, right? But we can still write subtraction as addition, yes? That we were like, well, there has to be a better way to write these out, because that's a lot of writing to have to write out the full expansion every single time. And there is, because you remember that what we've been talking about, what seems like forever now, is that when we are adding a whole bunch of stuff together, what can we write that as? A series, right? Using summation notation. So basically what we're doing here is we're taking Maclaurin and or Taylor polynomials and writing them as a series now instead. And those are called power series. Okay? So if x is a variable, then an infinite series of the form n equals 0 to infinity of a sub n times x to the n power of all of that stuff is called a power series. And the only difference from the second part is that I have an x minus c there, which means it's a power series centered at c, right? So the first would be a Maclaurin, the second would be a Taylor, because it's not centered at c. Now, something that we are going to have to think about is, like, what did we spend our last entire unit on? All of our convergent tests, yes? Which is now, this is a series, so we will also be able to say when this series converges and diverges. Yay. We don't have to remember all of our tests, though. We will just be using our ratio test. Don't get too scared, because it's really not that bad. Some of them get a little long, but it's not that bad. Now, one thing that we do have to consider, though, is that in order to be able to, like, write out this expansion, yes, which is a Taylor or Maclaurin, how do we normally get those? Like the old-fashioned way. You have to take a bunch of what? Derivatives, yeah. So if I can't take the derivative of something, or whatever we're trying to center it at, the derivative is undefined at that spot, we can't do it. So there will be some times that we cannot create a power series because the thing is undefined there, or its derivative is undefined there. So this says some functions shown below will not generate a Taylor polynomial at C because the function or one of its derivatives doesn't exist there. Determine which functions present a problem and explain why. So thinking about y equals the square root of x minus 1, are we okay to be centered at x equals 2? Yes. For the original, right? Our domain would be 1 to infinity? Yes, or maybe? Now, we do have to think about when I take the derivative of that, what would I get? Times 2, but yes. Yeah? So are we still okay to plug in 2 there? Yes, we are. And the more derivatives I take, basically this is just going to get, like, have exponents on it on the bottom, right? So we would be good. So this one, we would be able to take a Taylor polynomial centered at x equals 2. All right, what about part B? Why not? Correct. So what's our domain here? on the inside of a natural log has to be positive and it can't equal 0, yes? So I would have a 1 there to infinity, but that is not including 1, yes? We all agree with that. So I can't be centered at 1 because my domain does not include 1. Alright, what about cotangent? Centered at 0. So this is a midpoint. Why not? Yeah. So this is cosine over sine. Yes? And sine of 0 is 0. Yes? So that means that cotangent of 0 is undefined. So no. Or you could say because there's an asymptote. Either one. Alright, this next one should look familiar, right? Same as my one before. Am I okay to plug in -1 into my original? Yeah. Am I okay to plug -1 into my derivative? So I've switched the sign, right? But our derivative would work very similarly, yes? I would get 1 over 2 square roots of x plus 1. Am I allowed to plug in a derivative, or -1 into my derivative? Yeah, but a 0 where? On the bottom, right? So, what's my answer there? No, because y is not differentiable at x equals -1. What about my next one? Plug in 0 to my original function? No. What's my domain for this function? Yeah. Is 0 in that?
No. Nope.
Okay. What about my last one? Can I plug in 4 into my original? Yeah, if I take the derivative of that, I would just get -1 over x minus 3 squared, right? Can I still plug 4 into that? And then it would just be, right, the negatives are going to alternate. I'll get a bigger constant on top, but basically it's just going to be x minus 3 to the second, third, fourth, fifth, whatever on bottom. And so am I going to be okay to plug in 4 to all of those? Yeah, so we would be good for that one. Yes, no, maybe. So that's why we have to be particular about, sometimes we can do different functions, but we do have to be careful about where we're centered at. So cotangent, I couldn't be centered at x equals 0, but I could be centered at like pi over 4, yes? So like just because one function doesn't work for a specific x value, we can still move that accordingly depending on what we're needing. Now, you don't have to write this down. This is just us talking about it. So, notice that, okay, this is n goes to infinity of a sub n times x minus c to the nth power. Yes? No. Alright, so notice that my summation is in terms of n. Agreed? Which means that am I plugging stuff into my x? Just based on my summation? No. Which is why I write it as an f of x, yes, equals all that stuff. So this is where I would choose what I'm going to plug in for f. Agreed? So notice that what I choose to plug in for x is going to then change what type of series I have. It would also change if that series is convergent or divergent, which means that we will have a domain, okay, or like an interval of x values that power series will be convergent for. Are we all with me there? And a lot of the time, our goal is to figure out what that interval is. And the 3 different ways, I'm going to have this up here in a second so you don't have to write this part down, is, okay, so sometimes, okay, it will just be at a single point. Where is it always going to be convergent at? So what value could I pick for x that if I plug it in, it's always going to be convergent? 0, I want to get out 0, right? So I had 0 plus 0 plus 0 plus 0, right? So like, what if I plug in here gives me 0 here? C, right? So my function will always be convergent when x equals c, right? So that's why it will always be convergent at least at a single point, at c, okay? Sometimes there will be an interval centered around c, okay? So I could have stuff on either side, but c will be the center of that interval. And then sometimes, if it's just convergent everywhere, you will get the entire number line. So negative infinity to infinity. We really like those because they're nice to have to deal with because we don't have to worry about our restrictions on when it's convergent or not. Now, there's a lot of words on here, but for the most part, I want you to write down that we have 3 possibilities. That our series converges only at c, that it converges for some interval of x minus c is less than r, or the series converges absolutely, converges everywhere. So on my first option, I just have a point at c, because it is only convergent at that spot. On my second one, it's going to converge. Again, c is my center, which is why we've been practicing talking about things being centered at c, okay? And basically, we call this letter r, it's called our radius of convergence. And we call it our radius because basically it goes on either side of my c. So that's how I create that interval, is that I add r to c, and I subtract r to c. Notice that I have an absolute value around my x minus c, which is why we end up adding and subtracting. Now, the next part you don't really have to write out, because we can kind of think through it. Notice that if I have case 1, so I only have convergence at c, my r is 0. There is not anything on either side that's going to give me convergence, okay? If it is the third option, I'm convergent everywhere, so my r is infinity. Now, the biggest part that takes the most time is going to be that bottom note, okay? If you're just asked for r, it's actually pretty easy, and that's what we're going to look at an example of first. The hard part is, notice that on my interval on part 2, we do not have an equal to bar on that. Agreed? So when we're creating an interval, I'm going to have my bounds from whatever, -2 to 2, whatever it shall be. However, we don't necessarily know if it converges at our endpoints. So we have to check the endpoints if it asks for the actual interval. Now, if we just ask for r, we don't, because it's not asking for the interval, it's just asking for the r value. So we like those. Yes, no, maybe.
Yes.
Ready to look at an example of that? Okay, find the radius of convergence. Find the radius of convergence for each power series. My first one, I have n factorial times x to the n. So this time my a sub n is n factorial. Still just going to get numbers in front of that. And I am centered at 0 because I don't have an x minus anything. It's just x to the n power. Now, what test did I say we're going to use? Ratio 1. And the reason, if we think about it, remember that our conclusion statement is that our absolute value of, which one goes on top? No. The n plus 1, right? A sub n plus 1 divided by a sub n has to be what? Less than 1 in order to be conversion. Yes? And it already has the absolute values built in. So basically we already have a less than r built in and I already have an absolute value. So that's the one that we want to use because it basically already builds out what we need. Okay? So using our ratio test here, I have the limit as n goes to infinity as the absolute value of, again, our n plus 1 is what's on top. And just our original a sub n is on bottom. Yes, no, maybe. And again, what's going to happen is this limit is in terms of n. So I'm going to reduce some stuff and get an answer. And my answer should just be in terms of x's, which is why then we can use that to solve for our radius of x. So what would I do to simplify first? Yep. So n plus 1 factorial I can rewrite as, okay, and then x to the n plus 1 I can rewrite as, okay. So what reduces there? My n factorial and my x to the n? Yes.
Yes.
So maybe. Alright, so I'm left with so again, I don't really care a whole lot about that x, okay, but I do need to look at what is n plus 1 going to go to as n gets bigger and bigger and bigger. Infinity. So does it matter what my x is there? No, because again, x is just going to be a specific number for this power series, which means that this will equal infinity. Is there any spot that that's going to be less than 1? No. So, be careful, because we said that it's always convergent where? At my c value. What's my c value here? X equals 0, okay? And so it will converge at x equals 0, which means that our r is 0, because it is only convergent at my c value. Yes, no.
Yes.
So, next up, for this one, again, we're using our ratio test, so it's the limit as n goes to infinity of the absolute value. What's on top? 3 times
X minus 2.
yes, remember our n plus 1 goes on top. So notice that if we reduce that, my 3's are going to reduce, yes?
Yes.
Do you agree with that? And then this would be an x plus 2 to the n times x plus 2, yes? So our x plus 2 to the n will also reduce. So I get the absolute value of x plus 2. But again, remember this limit is in terms of n's. Do I have any n's left? No, so technically this is just acting as a constant, so my limit is just that. But again, in order for us to be convergent, what does that have to be? Less than 1. we get 3 and 1. Yes, I'm moving. Now, it doesn't ask us for the interval. I only need the interval to figure out, okay, what my radius is. So we're centered at 2. So how far from 2 did I have to go to both sides to get to 1 and 3? I'm centered at 2.
2. Wait, 1.
2,
1.
3, 1. How far did I have to go this way and this way? Just 1. So that means my R is 1.
If it's always centered at C, are we able to just drop the absolute value because it would give us the radius?
Not necessarily. Where do you want to drop it? Like here?
Yeah,
You drop
right,
it here.
right
The problem is though that I have to drop it here. I have to create a compound inequality because I also need the lower bound. So I don't just want to drop it and put less than 1 because then you're not getting that bottom bound. Alright, that's where we shall stop for today.